All right, we are live. Hi everyone, I am really excited to interview and host Finnur, CEO of Treble. I have been following his work and updates about developing Treble for a while, and it's very exciting and great to see like the progress of the development of this tool. So, Finnur, thanks a lot for coming on the show.
Thank you. Thank you very much for having me. I look forward to tell you about Treble and what it is that we're doing and where we're heading and so on.
Yeah. So before we dive into the presentation, can you share us like what are some highlights of your career from and professional journey from your academics till date?
Yeah, good question. I think I've actually been sort of here and there throughout the years. I worked as an engineering consultant for a few years in an engineering consulting firm in the building industry. That was very insightful within acoustics, and that was very insightful. And then I did my PhD together with Henning Larsen Architects, which is a well-known architect firm here in the Nordics, at least. And then I was sort of on the other side of the table, you could say, having come from the engineering side, and now I was on the architect side. So it's been kind of, that was very a different viewpoint. So it's been an insightful journey. And then before all of this, I was a software engineer also for some time. So it's been a lot of interesting things that's kind of led up to Treble.
I see. It's great to see the multidisciplinary aspect.
Right.
And like what was the moment where you decided let's go all in for Treble?
It was, so I founded it together with a good friend of mine, Jesper Pez, and who's also an acoustic engineer like me. We studied together at DTU some almost 10 years ago. And then we went our separate ways, sort of, but still always working with acoustic simulation, so sound simulation. And then there was just a time where we were at some, barbecue or something together, and we were like, I know a lot about sound simulation. You know a lot about sound simulation. Should we do something about that? Or, and then we decided to go for it. And, we applied for a grant here in Iceland from the Innovation Fund. That was a big kind of step. Okay, we're actually doing this. And then we got the grant, and then it was like, okay, there's no turning back now. Let's do this.
That's nice. And what has been the most challenging aspect about developing it?
Yeah, that's a good question. There have been many technical challenges along the way. It is quite complex stuff that we're working with, I would say. Sound in a space is a very complex physics phenomena, actually, and modeling that requires, pretty in-depth knowledge about physics and mathematics and computing. So on the technical front, there's been quite a few challenges, but then again, I've also been so fortunate to have a good support network, you could say, around me. I've had a lot of great collaborators throughout the years. For example, my academic supervisors during my PhD. So even though it's been hard, it's been kind of, a nice journey together with many collaborators. And then on the business side, or sort of more commercial side, there is I would say an ongoing challenge with sound and acoustics to get people to maybe think a little bit more about it and then take it into consideration. Sound is a very intangible or invisible phenomena, so it can be easy to neglect it, but then we usually regret it afterwards if we do. But so maybe those are two highlights of the challenges.
Yeah, like I could only imagine, like it's so important, but also there's a challenge of raising awareness and making people understand you got to start it at the beginning. And I could it's a great product, but like the market is not ready yet, so we are preparing for it. So
exactly.
cool. So I think now it might be a good time to dive deeper into Treble and showcase.
Sure. Okay. So I did prepare some slides. This is a kind of a slide deck that I've used before when presenting Treble. So I thought it would be an okay thing to bring it to this interview, so that we had something visual on the screen while we talk. And sometimes it's a bit easier to understand some of the technical things when there's something on the screen that explains it. But by all means, just shoot in comments and questions along the way and so on. So it's not meant to be a long monologue of just me talking. But yeah, so our company is called Treble Technologies. It's not very old. It's just a little over a year old. But so we're sort of an early stage startup, you could say. But our roots go back actually many years back into the R&D development and academic environment where our technology was originally developed. We have a tagline in Treble, which is enabling a better sounding world. We think that summarizes quite well what we're about. That is to say, we're developing software products that enable designers of the built environment, architects, engineers, interior designers, urban planners, etc., to better work with sound, understand sound in a more intuitive way, and hopefully lead to a better sounding built environment. Yeah, so I sometimes talk about the sound of architecture. That's what we're doing, and using this technology, virtual acoustics. So this presentation is kind of divided into three parts. First, I talk a little bit about sound in the built environment in general, just to put us all on the same page here, and tell you about some interesting research that's been done throughout the years on sound and acoustics. Then go on to talk about the technology that we're developing. And finally, we can end up with some demos and case studies of it being used in action. But just before I begin, maybe a bit more about myself. I've kind of already hinted at this in our introductory chat, but before I started Treble Technologies, I was a consultant in the engineering industry, software engineer at the telecom company here in Iceland. A PhD, did that together with Henning Larsen Architects, and then I was also a postdoc researcher for some time before starting Treble. And sort of my main sort of fields of interest, or at least from a sort of research and development perspective, are these things here. And I would say that sort of the sum of these things is kind of exactly what we're doing at Treble. All right. So sound in the built environment. There has actually been done a ton of research throughout the years that sort of shows quite clearly and unequivocally that sound, acoustics, noise, soundscapes, they do have a big impact on our health, on our well-being, on our productivity, and so on. And when these things are not in an ideal condition, when there's lots of noise present, when the acoustics are bad, which are sort of two sides of the same coin, then that impacts us in a pretty severe and negative way. For example, open plan offices or sort of modern office places, one survey after another is showing that something like 70% of people are actually unhappy about their sound environments in open plan offices. And research showing that when there's noise present or the acoustics are bad, then people's stress levels go up and their productivity goes down. Similar story is seen in educational buildings. Research showing that when the acoustics are bad, then students, they perform worse, both on sort of standardized tests, but also on various tasks like reading tasks or memory tasks, listening tasks, and so on. One research that I read was kind of interesting, that showed that when the acoustics are bad, then students, they judge their peers and their teachers less positively than when the acoustics are good. So that can have a pretty serious impact. In healthcare, there's been so much interesting research showing all kinds of negative effects of noise and poor acoustics. When we see, for example, extended hospital stays, when noise is present, we see more cases of rehospitalization, we see more pain medication usage, slower healing, huge correlation between bad acoustics and sort of cardiovascular health. So yet another example of having, of a scene or scenario where it's important to have good acoustics. And then when we go outside, that's a whole other kind of domain, but again, serious impacts of negative impacts due to noise. Like, for example, the World Health Organization, they say that noise is the second most harmful environmental factor affecting human health, just after bad air quality. And noise is generally on the rise across the globe. They say also that just in Europe alone, more than 1 million healthy life years are lost every year due to noise. So it is indeed a huge public health issue. And then last but not least, of course, in concert halls and cultural spaces, auditoriums and so on, it's desirable to have the appropriate acoustics. This hall that we see here is actually just a few hundred meters from where I'm sitting right now. It's here in Reykjavik, Iceland. Harpa is the name of the concert hall, or the building itself, and the hall itself is called Eldborg. This is designed by Henning Lassen Architects, and the acoustic consultant was Arup from the US. Very nice hall, if I may say so. All right, but so as I mentioned earlier, actually, Treble's history goes back quite a few years, and before just early 2020 when we actually started the company. So when we started the research work, that was around 2016. We sort of set out to address this question that I write up here. Can we develop some technology or some methods that can make sound be a more integral part of building design, such that we end up shaping spaces, doing space planning, selecting materials with sound in mind, or driven by sound, hopefully from the just earliest sketches and throughout the whole design process. And it's a kind of a tricky thing because sound is indeed an intangible phenomena. It's invisible. It's hard for people to relate to and to design it and work with it, both from a sort of optimization perspective and also kind of from a creative perspective, if you want to create some interesting or even you could say thought-provoking soundscapes. It's hard for people to do that. So we really wanted to develop some technology that helps with this. My project was my PhD project, which was sort of the initiation of this work, was actually started or initiated by Henning Lassen Architects. They were quite often running into problems with sound. They would design something that's, looks great and it works in various ways, but then sometime late in the process, some sound specialist would maybe be brought on board and they would say, sorry, it's all backwards here. We have to go back to the drawing board because it's going to sound terrible and so on. So they were kind of repeatedly running into issues with sound and acoustics and wanted to try and develop something that could, facilitate or address this issue. And that's kind of how my PhD project came about. And this led us to the development of what we usually call virtual acoustics, which is, this idea of both being able to just simulate sound and analyze sound in a very effective manner during building design, and also render it or experience it, so that we don't just have to read graphs and numbers, but we can actually just walk around a building model and experience how a building looks and sounds. So I say here that we're throwing around some big phrases. We're developing the building modeling technology of the future. But our idea is kind of fairly simple. We want sound to be an integral part of the 3D models that architects and engineers live and work in all day, every day, essentially, such that we end up evaluating our design, not just with our eyes, but also with our ears. This is kind of what our technology enables. It enables us to create these real-time virtual experiences where you can walk around the model, you can interact with the design, you can change things on the fly and experience the difference between different design options. And I'll come back to a bit more details here in a couple of slides, I think. Just 1 second break here. So this slide here illustrates, so if we take one step back and kind of think a little bit about what's going on behind the scenes, then this slide illustrates the process here. Ultimately, we need to do some simulation of sound to be able to understand it and design it and optimize it. And the process works in this way, that first we start with some input data to the simulation. We need obviously a model of the geometry in question, whether that's an interior space or an outdoor domain. We need some information about the surfaces in the space or domain, the acoustic properties of how different surface types absorb sound when a sound wave hits them. And we need some information about what sound sources we expect there to be present. We then feed this to a simulation algorithm that computes how sound propagates in the space, essentially how sound is radiated from the sound source, bounces around the room or the outdoor domain, and then reaches some listener or a receiver. And then the output of the simulation can be in various forms. We can get out just kind of graphs and numbers. For example, this parameter reverberation time, that's quite commonly used as a sort of indicator of acoustic quality or acoustic comfort of the space. We can visualize sound. That can be helpful in certain cases. For example, here, designing a concert hall and you want to design some sort of canopy here up, which reflects sound to all seats in the hall. Also, if you want to spot some undesirable echo patterns or things like that. But then maybe the most interesting part, arguably, is rendering of sound, so we can, experience how the space actually sounds. And our sort of take on it is kind of summarized here in this product that we're currently developing. It's still in development, I should say. We're planning to release it late next year. But we're already doing various pilot projects with all kinds of interesting people from the industry, using it in practice. And I'll give a couple examples of that later. But what we very much want to do is we want to plug directly into the workflow of the industry and into the tools of the industry. So we don't want to make a standalone tool, but instead we want to be a plugin into, like Rhino and Revit, perhaps other common 3D modeling platforms. At least to begin with, we're starting with these two. And this way we're hoping that the whole effort and manual labor that it takes to set up and perform an analysis of acoustics will be very, very fast and efficient. And hopefully that in turn leads to people doing it more, because it's not a whole thing to have to do it. Nowadays, it's a bit, if an architect is designing something, let's say in the rather early stages where the design is maybe changing a lot and fast, and things are moving at a fast pace, then if you need some input on the sound or the acoustics, then unfortunately very often it is that the architect calls up his acoustician and they get an answer two weeks later or something like that, because it's a very slow feedback loop. And that's not ideal, I would say, and often leads to the acoustics just being evaluated at the very end, because when the design is more or less set, and that's obviously not good, because then we can't really work with the design from the sound perspective. Okay, then our simulation engine, which is sort of the core tech of Treble, actually sits in the cloud. And the reason I mentioned the cloud is just because I want to highlight that in order to do accurate simulations of sound and to be able to produce these authentic listening experiences, then we need to utilize the power of the cloud, because these are pretty hefty computations that we're doing, and this would be very difficult to do with the level of sort of fidelity that we're working with without the cloud. And the cloud is also very attractive because you can, for example, ship off, if you have 10 different design options that you want to consider, then you can just ship them all off to the cloud and let the cloud do the crunching, and then you get all the results back at the same time, and so on. So it's a very powerful technology, obviously. And then what comes out of the simulation is kind of in two parts. One is more of a traditional analysis suite where we can, look at graphs and numbers, see some colored plots, etc., to assess the acoustics. And that's kind of then the interface of that is still here in the plugin in here. But then we can also feed the simulation results to these visualization or rendering platforms like Unreal, Unity, Enscape is another one we're interested in working with, and so on.
Finnur,
Yeah.
what kind of data format you need to export it to the cloud? Is it like OBGA 3DM file, or
Right.
the reason I
At the
asked?
moment, yeah, at the moment we're working with a 3DM file. And that's shipped to the cloud. And then we have our own meshing tool within the cloud, which needs, because we need to convert the 3DM model to a mesh, a kind of a computational mesh that we can then run the simulation on. So that's the way we're working now. We are, I would actually say that this is a very interesting question. We've done a lot of work on the sound simulation part and the acoustic engine and these things, and we're very far with that work. We're a bit shorter with the whole linking to the geometry and the tools here and so on. What we want is ideally to have a process where you have just your BIM model or your Rhino model, whatever, and just with one click of a button you can run a simulation, right? That's the ideal. But now it still is a little bit that you need to clean up the model a little bit and adjust it and so on before you can run the simulation. And so I'm just trying to say here, we're very much working on this part of the whole chain. That's kind of where our main challenge is, I would say, at the moment, actually. So it's very
Got it.
interesting. Okay. Here is a quick view of the tool, the way it works now. It's still very bare bones, I would say, because as I mentioned, we've mostly been focusing on the back end, on the core engine, but now we're just starting to dip our toes into, the front end and the link to the geometry and so on. But what we can see here is, let me just pause this a little bit here. So here we have Rhino. This is in Rhino, which I'm sure you're familiar with. Have some simple model of an open plan office, small open plan office here. This is an example. And then our tool is sort of a plugin into Rhino. And then you have the layer structure here from Rhino. And then we have our own separate treble layer, which is where you put in the relevant geometry and some parameters for the simulation. And then here in the plugin, you adjust some configurations for the simulation. You need to assign the surface properties that I mentioned earlier to the different surfaces. Again, this is kind of very bare bones at the moment, but still, we're able to run the whole process here. And then you put in a sound source somewhere in the space and a bunch of receivers. That's where the listener is positioned. There's some, I don't know if I should go into details. There's some details that you need to set here for the simulation, some parameters, and then you essentially just hit run, and the simulation goes to the cloud, and then you get back some results. Let's just take a look here. So here's a material assignment, creating the mesh, as I mentioned earlier, done in the cloud, and then hits run. And I will admit that we cheated a little bit there. It takes a little more time than just the 2 seconds there, but not so long, but still we cut the video there. But then here you get out some graphs and numbers, as I mentioned earlier, that kind of can describe the acoustics. It's still, I would say, what we're seeing here is more of an engineering tool, so more detailed, rather than a tool that's maybe more aimed at designers. So we're very much, our plan is to develop kind of 2 versions of the tool. One which is super detailed and super engineering-y, where you have all the little nuances and details that you can analyze and so on, which is aimed for the acoustic specialist. And this is kind of heading in that direction. This is our alpha version of that tool. But then we want to do another one, which is equally sort of powerful on the simulation engine, but with a much more simpler interface and kind of simpler usability and workflow, aimed more for people who are not specialists in sound, like interior designers and architects and so on, but to enable them to do some sort of evaluation of the acoustics and at least push the design in the right direction. And then you probably won't see details like, these technical things here that you need to adjust in the simulation, and the results will be more simple and so on. But I thought I would still show you where we're at the moment.
Yeah, I was thinking it might be interesting, like sometimes we compare different materials during a simulation. So if in a drop down I can select a couple of materials, and on the cloud I can like do parallel computation and do a
Absolutely.
comparative analysis report.
Exactly, exactly. That's one of the big things that we would probably design and optimize is it's the geometry, the space planning, and then the materials, and being able to ship to the cloud various versions of this and then get back results and compare them in some simple way.
Hmm.
That's the ideal, I would say.
Hi, Finnur. Richa this side. So my question here is like when we talk about insulation and material, are we talking about the walls and stuff? Also, are we talking about lights, which has some acoustic conditions or some paneling? Do we talk in that detail?
Mm, we try and take into account all the surface properties, you can say, in the space. Lighting per se, we don't evaluate, but you can, if you have some absorbing free hanging fixture, whether that's a lamp or some free hanging baffle or something like that, we can certainly take that into account. Does that answer the question?
Yeah, like how to in this right now in this process, how do we give that input that yeah we're using that certain light? Will this automatically adjust and understand that yeah that light has a particular material, so it has some absorption capacity?
Yes, absolutely. Yeah, so you can put that into, then you would have to, at least the way it is now, you would have to draw in the fixture or yeah, the lamp and assign some material properties to that. Then it would take that into account. Very good. Okay. Here's a quick overview of the different tech sort of key features that we've developed. First of all, the simulation engine. So we've done a lot of research into developing actually a totally new way of simulating sound and how sound propagates in a space, which is much more accurate than what's been previously possible. And that is enabling us both to create these authentic listening experiences. So it's been kind of difficult to do that up until now. You can certainly do sound in a 3D model. For example, video games have had that for many, many years. But if you want it to be physically or sort of close to reality, because ultimately we're of course designing reality when we're designing buildings, that has been very difficult up until now because the fidelity of the simulations just hasn't been there. But this is work that we did. We teamed up with leading scientists in the field of computational mathematics and wave simulations and ended up developing this very new approach to simulate sound, which enables this. Then we have a whole system here, which is what enables us to take those accurate simulations and experience them in the audiovisual virtual experience, in a real-time experience where you can walk around, interact with design and so on. A whole other world, which I won't go into the details of, but I spent a lot of time during my PhD researching, was how different materials absorb sound. For example, the lamps that we just discussed, it can be quite complicated how material or buildup absorb sounds, and to incorporate that in an accurate way in the simulation. And then the last part is the part that we admittedly have come shortest with, but still are definitely making good progress on that front, is to link directly to the 3D models, so the whole workflow is seamless. Here's just one illustration of which sort of compares the way we simulate sound compared to what's typically done today, for example, in video games and the few tools that are available for sound design in buildings right now. Our approach is what is called a wave-based approach, where we actually solve the physics equations that are involved and capture the wave nature of sound. Whereas the current approach is what's called ray tracing or geometrical acoustics, where we essentially neglect the wave nature of sound. You can, for example, this is meant to be like an open plan office here. You can, for example, see how sound bends around this partition wall here, whereas in the ray tracing approach, it doesn't do that. So that's, yeah, maybe a bit technical discussion, but very interesting still. Here is just one example. I thought this was kind of cool, of which compares these two approaches to simulating sound. Again, it's quite engineering-y, but let me show you real quick. We have this is a setting of an experimental setting where we have a sound source in this, what's called an anechoic chamber. That means that, all sound is completely absorbed when it hits these walls. So it's just kind of a single reflection. Here's a microphone. So there's the direct sound that goes to the microphone, and then there's one reflection off of this pretty complex geometry. So maybe a bit of an arbitrary setup, hard to relate this to reality, but just a way to evaluate how we can simulate some complex geometry. And then what we see here, if we focus first on the right, this was part of a research and a part of a paper that was published in the Journal of the Acoustical Society of America a couple of years ago. Then you can see the measurement result here. We don't maybe have to understand exactly what's going on here, but this is what's called the frequency response between the source and the listener. It's this black curve here. And then they tried all kinds of different simulation tools to see if they could capture this black curve with the industry standard tools that are available that are all based on this ray tracing paradigm. And as you can see, actually none of them are able to model this kind of complex geometry. But then when we use our wave-based approach, we are able to capture this with pretty good detail. So that's an indicator of the fidelity of using this wave-based approach. Okay, that was for a static simulation, static case, but it gets even more important when we start listening to the space and walking around the model and experiencing it, because these wave effects have a pretty big impact on the way we perceive sound. So these are two kind of well-known problems that illustrate the issue here. One is called, for example, the lamp post problem. So imagine you have someone making a sound over here, and then you're standing here, and there's just something very small that directly blocks the line of sight between you and the source, like a lamp post. Then in reality, obviously, if you have a lamp post between you and someone that's talking to you on the other side of the lamp post, it has no impact on the sound whatsoever. Sound just kind of goes around it. But if you don't capture this wave nature of sound, then you would get a very unnatural kind of blocking of the sound when the line of sight is blocked. But when you move your head just a little bit to the left, you would get this jump in volume because now the sound is there. It's because, but in reality and with the wave-based approach, we capture this kind of bending around obstacles phenomena, what's called diffraction. And then the whole listening experience is more natural. And then an analogous problem, you could say, is when we have a big surface with a small slit in it, then again, you would get this unnatural jump in volume if you don't capture the wave nature of sound. And this is, as I mentioned, due to diffraction, which is this phenomena of sound waves bending around obstacles and bending around corners, the reason we can hear someone that we cannot see. Okay, and then now I'm almost done with the technical part here. It's a bit going deep, but this is just to illustrate how we actually generate these listening experiences. Then we do the simulation, we pre-bake the results into the model. And then during runtime, when you actually want to experience it, you walk around the model, and then there's a real-time processor that's sort of taking the pre-baked simulations and portraying them back, taking into account where you're positioned in the room, what the orientation of your head is, and so on. And then if you want to interact with the design, you're essentially switching between predefined or pre-computed scenarios, predefined design options. Okay, now we're done with the nerdy part, the technical parts. We can hopefully come down to earth again and take a look at a couple of examples of case studies. The first one I want to tell you about is something we did together with Henry Lassen Architects. We, of course, have a very close connection to them. I did my PhD with them and so on. And this was a city hall in Uppsala in Sweden. It's a part renovation and a part new build. So they kind of expanded the size of the building fourfold or something, I think. So it was a very small building beforehand, then they greatly expanded the size of the space. And it's mostly office spaces, but also you have, for example, this very large, nice atrium space there in the middle. There's also a nice big auditorium here. It's kind of an interesting building. I think it's kind of a building within a building. So you have the outer building, which is kind of surrounding this big atrium space, and then you have an inner building or interior building here in the middle, which has the main city hall and so on. So it's a pretty cool design. This atrium space is actually open to the public, so people can walk through here. So we can expect at times that there will be a lot of people present in the space. There's a cafe in here. There is, yeah, you know, at times politicians will be coming out of the main city hall. So it's kind of tricky from a sound perspective. And then on top of that, we have, you know, on the material front, we have just glass everywhere, glass ceiling, hard floor. So again, tricky space. So what we decided to do was to do a virtual mock-up of this space during the design process, where the architect and the client and all kinds of stakeholders could experience different design options. They could play around and test out different things and see what worked and what didn't, what impact it had on both the aesthetics and the sound, and yeah, help them make an informed decision. And it proved to be very valuable in the process, and helped everyone understand the importance of taking sound into consideration here, and yeah, and kind of understanding how far we had to go in order to make the space comfortable. So I will show you a video from the virtual mock-up. In the video, you can see the user walking around the space, and with a click of a button on her hand controller, she can interact with the design. She can, for example, change what we call the occupancy in the room. That's how many people are present in the room. It going from being completely empty to just a few people, a bit more. And then when there's full occupancy, we actually even put a little jazz band here playing at the cafe. That's actually our CTO, Inkimar, who's playing the saxophone on that. And then she can change what we call treatment, which is the acoustic treatment, and essentially just switching it on or off. So I think A means it's off, so then it's reverberant and noisy, and then B means it's on, and then it's more comfortable and sort of calm atmosphere. Then I think she also claps in the space, and then you can hear the different reverb in the space essentially. Then she walks into the main auditorium here, and there she can select some surfaces and change the surface finish to see the different visually and also experience on the sound part. And even changing the glass type here that separates the main auditorium from the atrium, and sort of assess the sound insulation, how much sound goes through the glass. So let's take a look. I hope it speaks for itself. I should mention it's meant to be listened to in headphones. So yeah. Now she'll go into the auditorium.
Made up of words that come to me spontaneously, words that speak the honest truth. Expect from me nothing else, because I do not believe, fellow Athenians, that I should be appearing before you at my age, behaving like a child, trying to construct over-adorned speeches. This is the only thing.
She's turning off the sound source so she can hear the sound from outside. Then she switches and you can hear the level go down. And come back. So this is one of the early pilot projects that we did. Still things are in development, and you know, all kinds of aspects that we would like to improve, but I think it shows the idea of this virtual rendering part of our offering quite okay. One nice example of an outcome of this work was that we ended up designing these wooden frames which were incorporated into every element of the glass facade that surrounds the space. And these frames have the dual function of both just looking very good, I think, and then of, absorbing sound. So we have some sound absorbing material here behind. This was a big part of what we ended up doing to help ensure a good environment in here, along with some other things too. But I just think this is a nice example of what can happen when we think about sound in the early design stages. Then we can actually incorporate the sound design into the architecture, as opposed to it just being something that we kind of plaster on afterwards, Okay, this is another example also with Henning Larsen. This is an old office building in Copenhagen that was being renovated, going from traditional old style closed offices to more modern open plan offices. And the client here, he was very concerned about sound, people's ability to concentrate and focus and have privacy and so on in these open plan offices. So we did a virtual mock-up actually during the competition phase to kind of illustrate to the client that we were taking sound very seriously and thinking about these aspects. And so again, I'll show you a video from a virtual mock-up where we show all the different things that we had incorporated into the design to think about sound and make the sound environment better. For example, we put absorbing material in the ceiling. We put absorbing material here into the walls. We put dividers. We put glass partitions to break up the space into smaller segments while still keeping sort of a nice visual openness, you can say. And yeah, in the video, you'll see the user being able to switch on and off these various aspects that we incorporated into the design and experience the difference. So let's take a look.
Nej, det var faktisk logistikken, der var det allerstørste.
For I rev bygninger ned på Amager og sendte murstængler til Nordjylland og fik
det er min skyld. Vi udviklede...
Right. Okay. Here's another project we did together with Kierkegaard. Kierkegaard is a acoustics consultancy in the US, specialized in doing sort of performance halls and concert halls and so on. So what they are interested in is very high fidelity, detailed simulations of the acoustics, more like an engineering optimization task, and designing kind of, these high level concert halls where they need to be sure, going very much into the details. For example, you can see here in this model where they're designing these kind of diffusing wall structures to reflect sound in a certain pattern and so on. And then these wave simulations can be very insightful to optimize those things. This is more of an analysis rather than this rendering. I just wanted to give an example of that. Yeah, and I think this is my last slide. I sometimes like to mention this, that we have developed in Treble this technology of rendering and simulating and rendering sound in a very accurate way and of producing very authentic listening experiences. And we're very much focused on the building industry at the moment, developing tools to enable architects and engineers to better work with sound. But we do also see that this technology could be useful in other industries too, where it's desirable to have authentic or realistic sound, whether that's video games, all kinds of VR applications, or when you're designing, the acoustics of a car cabin, or or some audio products. So, you know, just to mention, just kind of between us, that we see some applications beyond just the building industry. All right, that was it.
Thanks a lot, Finnur. Like it was incredible presentation. I'm like doing virtual round of applause for you. It's amazing work, and it inspired me a lot based on the technology you have developed, the case studies you have. You, I could foresee the impact one could make using this technology. So
That's good to hear.
incredible work.
Thank you very much. Thank you for your kind words.
Yeah, and also like the UI, not only in Rhino but also in VR, is very intuitive, and it also like creates more curiosity on designers' end to try out different options and feel it,
Right.
and
Right.
maybe also one could present to clients and see, okay, like if you choose this material, these are the implications, and if by adding some more layers, you could maybe pay more, but you are creating a totally different experience.
Yeah, exactly. That's exactly what we hope to do. And this rendering part of it is very much about, you know, communicating acoustics to stakeholders, you know, because it is kind of hard to communicate. And, you know, when I was a consultant for a few years, was always running into this problem, you know, that we have design option A, which is this curve on some graph. And then we have design option B, which is a slightly different curve. And then you take this to people and they're like, I have no idea what these curves mean. So I'm going to go for the cheaper option. And I'm like, no, please go for the other curve. It's slightly better environment. And they're like, you know, can't really relate to those graphs and numbers. So we're hoping to address that issue with this.
That's great. One question I had was, since you have like the compute on the cloud for the simulation, are you envisioning like opening for API where other applications could call and interact?
Absolutely. That's very much what we want to do. And we think that this is definitely the where the industry in general is heading, right? We want to make a platform for others to tap into and, you know, do things that we couldn't even think of doing, you know, with our technology. That's very much our approach here.
Yeah. And when you were sharing use cases about outside AEC, I was thinking uh, in the metaverse, it could like create a whole new experience by
Yeah,
integrating this. Yeah.
exactly.
So one technical question I had is, when we
Mhm.
compare like state of the art method or using ray tracing versus wave based,
Mm.
uh, is it like I am assuming like wave based is having like more compute with non-linear analysis. So is it
Mhm.
we are getting more accuracy based on the like more accurate analysis we are doing?
Yeah, exactly. And, you know, it does come at a price. It is computationally more heavy, the wave-based approach, and that is sort of the reason why these methods haven't really found widespread use in industry yet, is because they're considered too heavy. You know, they've been in the academic world for since the 90s or something, where people like researchers have been testing them and developing them further and so on. But you know, ray tracing can be very efficient, but wave-based is you need to perform more computations. But that's exactly the main technical aspect of my PhD research, was addressing that issue and trying to come up with a way to make it practically feasible. And then it was a combination of these modern computing clusters, GPUs, clusters of GPUs even, combined with kind of latest and greatest numerical methods, the mathematics methods together. And then we were able to accelerate the process by something like a factor of 1,000 compared to using, you know, state-of-the-art methods and a very powerful desktop computer. So that's what enabled us to make this practically feasible. Yeah.
Yeah, like, and I totally like agree. Like currently we have like the GPU compute and cloud based like services. So there's no reason why we are not taking advantages of the accuracy we are getting
Yeah,
from this method.
exactly, exactly.
So Sujay has a question. Are there any preliminary guidelines a designer can keep in mind before designing an acoustically sensitive space?
Yes, absolutely. And that's kind of, I mentioned earlier this idea of doing kind of two versions of our tool, one which is super nerdy and engineering-y, and the other one which is maybe a bit simpler. And in that simpler version, it's still, don't get me wrong when I say simpler, that it's not powerful or anything like that. It's supposed to be that, but just kind of maybe a bit easier for someone to use who's not very much into the details of sound. In that version, we would have those guidelines incorporated, and then you could compare your design against the guideline in a very intuitive manner and get even feedback on like, okay, maybe if you consider doing this to your design, adding sound absorption here or changing the shape or whatever, and then you come closer to fulfilling the guideline. So yes, absolutely. There's been a lot of research done throughout the years, and it is, I would say it depends a little bit on what space type we're talking about, but generally speaking, we know what we need to do to make a space sound good. So it's more of having it actually done.
I see. I just had a thought it might be like once more and more people like start using it and have like data for this scenario, this material works best. It could be like AI recommender tool where okay, you have this space, you have this volume, maybe this top three materials you could test out, which might perform higher than other materials.
Absolutely, absolutely. I would think that's a logical next step somehow.
I
I
see.
have a question here.
Yeah.
So, like when we are talking about treble, so do it help us in, like with these automation or with these calculations, do we also get the support from, like one-on-one support helping us out saying which material to use or not, or like, to give a guarantee, like, yeah, this is correct. So do we have
Yeah.
something of that sort?
Yeah. Yes. So we're hoping that we will have, a very strong, what should we say, catalog of guidelines and tutorials and videos and so on to help people help themselves on this, and then absolutely a support network as well, if people get stuck or if they need guidelines or things like that.
My point of questioning this is like when we go as an entrepreneur question. So when we go to a company and say that, yeah, XYZ, we'll give you this service, they may not be, 100% trusting us after even, we show them the use cases or any which way. So how do we make that trust happen? That okay, we will do it 100%. Either we give some technology engineer to them, like this will be our 100% support. You call him, from this number, this time to this time, and then this help can come out, because they'll be like, okay, we can go to our engineer and that he will study the graphs and tell us why to use technology over it. So these
Yeah,
questions, how
yeah,
you deal with that?
yeah. That's a very good question. Something we need to think about. I think we have to build up trust over time, and maybe through good, I think especially for the architect side, through good early adopter partnerships and so on, where we have kind of proven cases with trustworthy names and trustworthy big projects and so on, that we indeed, it works and we've managed to add value, we managed to help the process and so on, and that way kind of build up trust over time. That's at least what pops to my mind when you ask this question, some kind of approach along this path.
I see.
I think,
Um,
yeah.
you mentioned like at the beginning about sometimes the way spaces are designed for acoustic purpose in the 3D model versus in reality sometimes it doesn't perform that what it was designed for. So
Mm.
curious to know like what are the major reasons sometimes there is differences between the actual performance versus like simulation. Is it like
Mm.
construction tolerance or just
Great question. Um, there are a few big ones, big issues, I would say. One is the simulation approach itself, this kind of ray versus wave approach. When we neglect the wave nature of sound, as is usually done today, then we lose a lot of information or fidelity, and that can definitely cause big discrepancies between simulation and reality. This is particularly happening in the lower portion of the frequency spectrum, where wavelengths are long, because then we get more wave effects. That's one thing. Another thing, which is, I would say these are two big things here. One is the wave nature, neglecting that, and the other is the material input data. It's not the industry standard approach to describe surface materials and their acoustic properties is not a very thorough approach. It's not a very comprehensive or detailed measure that's used. It's what's called absorption coefficients, which are used. So there is both the measure itself doesn't include all the necessary information, and then actually the way it is measured in a lab is not a very ideal process. There are tons of people working on this issue, by the way, it's well known in the industry, but I would say that these are the two big things: uncertainty in material input data, and then the calculation engine itself. Construction tolerances is a good thing to mention too. Do we build precisely what we design? Usually not exactly, so that can be a factor too. And I, back from both from my as an engineering consultant and then also during Henning Larsen work and so on, I've seen many cases where what we get out is actually quite different from what we predicted. So it's a big issue, and it's becoming more important. Sorry, I keep talking on and on here, but it's just a good question. I have a lot to say on it, but it's becoming more of an issue because now various standards and regulation requirements are actually requiring people to measure after a space is built. So then you can't, 10 or 15 years ago, you could just say, I calculated this and it's supposed to be good, and then you're done. But now it's like, we will actually check up on whether it's good or not. And if it's not good, then you don't get your BREEAM credits or whatever. So.
Yeah, I think like the testing, like post-occupancy testing data will also be crucial, because if you're trying, let's say, a totally new material, there might not be enough test results, or like so that this data can reinforce some assumptions one might have. So
Right, absolutely.
yeah. So I'm curious to know, like, I don't have that much of acoustical background. We did like basic courses on how like to compute sound, but I'm curious to know, in scenario where, let's say, you build a building, it's not working well as per the acoustic performance. Like, what are post occupancy like solutions one could implement that, okay, let's make this space better?
I would say generally, unfortunately, it can be difficult to remedy acoustic issues after, like you say, post-occupancy. It's definitely desirable to try and foresee the issues during design, incorporate the relevant measures during design. That's way more cost efficient and just a better approach. Sound, for example, sound insulation issues, those are very hard to deal with after the fact. When I'm answering this, a case comes to mind. Actually, this office building I'm sitting in right now, there's a gym right below me. And the building was not designed, thinking that there would be a gym there. And there's just been endless issues with trying to mitigate the noise coming from that gym, both the weight dropping and the whole building shaking, and then all the boom, 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 music, So they are trying some things, and but it's very difficult, I would say. Room acoustics, which is more sort of sound within the space, is maybe slightly, you can do a bit more, adding sound absorbing materials into the ceiling or onto walls and so on, can help a bit. Depends on the case, how much you can do and so on. But yeah.
I see. One interesting phenomena I recall, like when I was working as a structural engineer, like we used to perform like vibrational analysis of a slab.
Okay.
And so I now I foresee it's not only architectural material selection and geometry, even like you might need like some structural engineer to like design whether the flow loads and the vibration frequencies like properly
Absolutely.
taken care. Because
Yeah.
I hear some sound from my like second floor guys sometimes.
Yeah, exactly.
So I'm not super sure, but is there any numeric comparison between like accuracy of wave based versus ray traced? Like
There has been some, yes, some papers out on that. We in Treble are also sort of building up a database, you could say, these days, to compare the different simulation approaches. This example I showed during the presentation where you had this kind of weird geometry and a sound wave being reflected off of, this is one example. But yeah, we have some, but we're building more, I would say.
got it. And what will be your piece of advice for architects during the design stage while for selecting materials? And what are some mistakes we often make in
Mm.
selecting materials?
Mm. Um, I think the sort of a good rule of thumb is to try and it depends on the space type, of course, what we're talking about, but good rule of thumb is to try and incorporate a decent amount, square meters or whatever, of sound absorbing materials into your space. You know, again, depends on the space type, but maybe try to go for if you have 100 square meter space, to try and have 100 square meters of sound absorbing material, so either covering the entire ceiling, for example, or something. That's an okay rule of thumb. Another rule of thumb is to try and distribute the materials. So I just said put it all in the ceiling. Actually, that's not ideal. I would rather have that you would somehow distribute it a bit more across the space and have something on the walls or on the floor, or some furnishing and so on. That's on the material front, maybe that's an okay rule of thumb. Then, acoustically speaking, some general things are we tend to like irregularity of shapes and furnishing and so on. So the worst thing that we have is completely empty box room. That sounds terrible. So if you can tilt the wall, or if you can add furnishing or have curved surfaces and so on, that tends to help a lot. Of irregular surfaces. Then space planning is a huge issue too, which is maybe overlooked. Generally we don't want to overload spaces. Yeah, something to think about.
Got it. And from your experience, what are some programs that are most difficult to deal with in acoustic, like in terms of atrium, concert hall, like?
Mm-hmm. Actually, the first thing that springs to mind is the open plan office. It's it's a relatively normal, common space. You would think that it wouldn't be a big issue, but it is very hard from a sound perspective to get that to function well. You have so many different types of work being done that require different sound environments, and then making it all function while also thinking about all the other different design parameters, lighting and ventilation and space planning and aesthetics and all. It is quite challenging. And one survey after another showing 70% of people are unhappy about sound in open plan offices. So we definitely should be doing better there. Yeah.
Got it. Yeah, like it's not that comes to my mind when like for dealing with sound in open house, but like it's a big issue. Yeah. But,
Yeah, exactly. Yeah.
yeah.
People tend to think about acoustics, then they think about concert halls, right?
Yeah.
And again, it's hugely important to have good acoustics in concert halls, and lots of details to think about there. But these bread and butter cases, classrooms, hospitals, open plan offices, that's also important.
Talking
Got it.
about typology, I have a point. Like Did you ever try to think for meditation halls or some spiritual retreats where we can just go into the mind of people and use sound for various concentration purposes? It would be
Mm.
really interesting one, I guess.
Yeah, it's a very good point. I've never thought about that, but yeah, definitely interesting and kind of yeah, this makes me think of soundscape design. Not sometimes acoustics are very much just thought of as being about reducing sound, minimizing sound, but that's not the whole purpose, not at all. It's actually to create the right soundscape. Sound can be pleasant, sound can be helpful, sound can be motivating, and so on. And like you mentioned, these spiritual scenarios and so on, where you have the kind of some specific sound environment that's kind of very helping you get into a certain state of mind and so on. That's yeah, I think that's going to be more and more thought of in the future, that where sound, I would rather talk about sound design in during building design and not just noise reduction or something like that.
Yeah. This might be a bit off topic, but I was thinking sometimes I have seen people like white noise or like general ambient noise in a space. I don't that
Mhm.
helps them focus or being productive, or some music. So what if like there's some music in open space? Like, is there any study where that has been
Yeah,
correlated?
yeah, absolutely. And this is an emerging field, I would say, this kind of soundscape design approach. Um, yeah, definitely. A lot of interesting research showing, the positive impact of having what people generally perceive as pleasant sounds. There is, of course, some individual variability between people, but overall, we tend to like bird songs, and we tend to like water fountains, and we tend to dislike a jackhammer, so yeah, by having those pleasant sounds present, it has a positive impact. But it's a fine balance between, again, the individual variability, the type, and I'm thinking about an open plan office, for example, the type of work that's being done, and so on, what kind of atmosphere you want to set. So it's nuanced. And
Got
then
it.
the white noise thing is you mentioned, that's commonly employed, I would say, what's called sound masking, to which sounds kind of backwards, that you introduce more noise to a space to make it more comfortable. But
Mhm.
that's because it's better to have some sort of background noise that's not where you can't really make out what's being said, versus the most disturbing thing is, of course, when you're trying to write an email and someone's just talking next to you, and you just start writing what's being said instead of what you wanted to to say yourself. So yeah.
Yeah, I don't know if this is a big issue, but sometimes people like type very like make some very loud noise while typing on a keyboard, and it's, let's say, imagine an office where everyone is like
Yeah, exactly. Yeah,
You have to
my
feel proud about it.
yeah. Yeah. And the Treble staff is a mixture of acoustics people mostly, and software developers. And most of our software developers have a very strong opinion about the type of keyboards that they use. They want to use these mechanical keyboards that are super noisy. But yeah, so I know the feeling.
okay. Sujay has a question. In cases where sites are located next to industries or airport, what's your
Mm.
approach to locking out external sound?
Good, great question. That's, of course, a very common scenario. And, as we're seeing, at least, in many cities where people are not trying to expand the city, but rather make it more dense. So, the plots that are left tend to be next to a highway or next to a railroad, or something like that. So it's a very common problem. There are many solutions that exist. And yeah, but generally speaking, we need, yeah, how do I go about this? Sound, the basic rule of thumb with sound insulation is mass. Mass helps you, right? The heavier the construction, the better sound isolating it is for airborne sound. So, you know, thick concrete walls are obviously better than lightweight timber walls. But then there are lots of interesting solutions that have been developed throughout the years where you can have, for example, some certain layers of buildups and so on, where you get a very good sound insulation with much lighter materials than what you would otherwise need. Yeah, good glass, you know, buildups, relevant glass buildups, relevant wall buildups, and so on are important. Then there is the aspect of ventilation. You know, if maybe you have some super isolating wall and glass, but then you just open the window and then it's, you know, all for nothing. So there are also ways of getting natural air in through a facade without getting the sound through. So there exists good solutions there. And then of course, if you have mechanical ventilation, then that also helps. So
Yeah, that's great to know. And what are some technical aspect which architects should know so that they can design better, like spaces better in terms of acoustic? Like what terminology or theories?
Yeah, there are, for example, some acoustic parameters that are commonly used that might be helpful for if architects are interested in this to familiarize them with. The most common one is this reverberation time parameter that I mentioned earlier. Generally speaking, the longer the reverberation time, the worse the acoustics, although there are some nuances to it, but that's one which is very good to know. Then a couple of others are also commonly used, like STI, speech transmission index. That's kind of how well speech goes from a talker to a listener. So in an auditorium, you want the STI to be as high as possible. It's a rating from 0 to 1, 1 meaning you can perfectly hear everything, and 0 meaning you can't hear a squat, and then something in between. So that's a good one to familiarize on how STI, you can make STI maps of spaces, you know, how some speech goes through space. But then, for example, when you have an open plan office, then maybe you want your STI to be low because, you know, you don't want to hear clear speech going through all the office space. So these kind of main acoustic parameters might be worthwhile to familiarize with, I would say.
Awesome. Now before we end the interview, I have a few light questions to ask.
Okay.
So what cities, which cities in your travel bucket list?
Oh, yeah, that's a good question. I've traveled mostly in Europe, so I want to go outside of Europe, let's say. The US, South America, eastern part of the world. I have more or less that yet to be covered. So that's on my bucket list. There's no one city that comes to mind, but these areas of the world, I've been to a few of them, but definitely not enough, you know.
I see. Is there any book which was quite influential in your life?
Oh, I'm such a geek. The books that come to mind are just books about mathematics or acoustics or things like that. Yeah, I must admit, it's been a while since I read like a good novel. So yeah, I would say Jan Hesteven's book on the discontinuous Galerkin finite element method. That's the book that changed my life.
I see. Sujay has an interesting question, like, which is the most silent city?
I actually heard somewhere that Reykjavik, where I'm living right now, is supposed to be a very, very silent city, but I'm not sure I fully agree. I think it's, yeah, I think there's quite a lot of noise here. But if you go outside the city, then obviously, no, Iceland is a very quiet place. It's very not densely, sparsely populated, you know, except for the the greater Reykjavik area here. So there's lots of silence in Iceland. I lived in Copenhagen for 6 years. I actually thought I was impressed by how, you know, considering it's a pretty pretty dense city, the city center part, but it's all almost, or at least a lot of biking and not so many cars. So that very, contributes to a more pleasant soundscape there.
That's right. Now it's on my bucket list to visit.
Yeah. I
So,
definitely recommend visiting Iceland. It's a unique place.
mhm. If you had like unlimited time and resources, what is one thing you would like to do?
Wow. I am super engaged in treble at the moment. So I would just like to put more resources and more time into continuing our efforts there. I think that has all my mind, or big portion of my mind and my yeah, abilities at the moment. I think that my answer goes there.
I see. Yeah. Uh, we could see the passion you have for travel, and it's a great product. Um, okay, I totally blanked out what I was gonna ask next.
That's totally fine.
How the
Cool.
typical day look like?
Oh
Sorry,
yeah.
thanks.
So Mayur will ask this question.
No, Richa got it. Like I often ask, like, how does a day in your life look like?
Right, right. So I have two small kids, a 4-year-old and a 1-year-old. So that takes up quite a lot of energy, sort of, or time outside of my working day. So typically, it starts with an hour of action with those guys, getting them dressed and fed and ready to go to kindergarten. And then usually it's me who drops them to the kindergarten, and then I go to work, and we work here. We're 8 people in Treble at the moment, and then we're adding 4 more, so we'll be 12 within a couple of months. We have a very nice office here in a sort of innovation hub. So there are many startups together in this building, and then we spend my day here, and then go home. Again, action with the kids for a couple of or 3 hours maybe, and then I'm usually kind of wiped actually after a day of that. But my hobbies include, when I get the time, I try to go to the gym or to do some physical activity, because I am kind of sitting by the computer most of the day. And then I also like to play music, although I don't have as much time for that now as I used to, but still do that occasionally. That's very nice.
They should be in the table presentation. We should know them.
Yeah.
And what kind of music do you play or like?
Yeah, I play the guitar and various types of music, but mostly sort of rock and roll. I like, that's my classic go-to.
Nice. So my last question is there anything about the industry which frustrates you?
I think frustrated is maybe a bit of a strong word, but there's room for improvement here and there. Yeah, maybe more interdisciplinary collaboration between all the different fields, better tools. The whole BIM world seems a bit that there is room for improvement there on this whole way we work with geometry models and building models, and the tools that are available there. Seems like, yeah, there's some room for, I imagine after 10 or 20 years of development that we will have a much more efficient way of designing and communicating designs and so on. So I think that's exciting to be a part of that.
I see. Thanks a lot, Finnur, for your time to do this. I had a great time. Thanks everyone for watching.
Thank you, guys. It was very fun talking to you. Yeah, thanks.
Have a nice rest of your day.
Yeah, thanks. You too, guys. Bye-bye.